Hello and welcome back. So in the last video lecture we have learned the modular arithmetic. So now in this video we are going to learn the Chinese remainder theorem. So it's a very old theorem. It's invented in the 3rd century. So let's see that this Chinese remainder theorem. So this is very useful in cryptography. Especially in the RSA. Next video lecture is on RSA algorithm, public key cryptography. So it's very useful in solving some complex problems of cryptography. So let's see the Chinese remainder theorem. Chinese remainder theorem, sometimes it's known as CRT, Chinese remainder theorem. It says that suppose the GCD of m and n that is equal to 1 with a given integer a and b, then there exists exactly one solution. So this is a special case of this Chinese remainder theorem. Special case. Okay, so there is exactly one solution of x mod m into n to the simultaneous congruence, that is x congruent to a mod m and x congruent to b mod n. Okay, that means that is also congruent to x congruent to x mod, so this whole equation, fine. So this whole equation. So there would be only one single solution for this according to this Chinese remainder theorem special case. So I can rewrite this in the form like x is congruent to a mod m that is congruent to b mod n that is further congruent to x mod m into n, and this condition holds only if m and n are co-prime, which means GCD or HCF of m and n that is equal to 1. So then this whole condition is true. So now we are having these equations like x is congruent to a mod m, x is congruent to b mod n, x is congruent to some this kind of form. So now whenever we are having this like x congruent to a mod n, x is congruent to, okay, let me take the same notation, a2 mod n2, x is congruent to so on, fine. So now that is our special case. The thing is that how we are going to apply the Chinese remainder theorem to solve for x. So now the very first step, we are having the 4 steps in the Chinese remainder theorem. The first step is we are going to find a capital N that is equal to n1 into n2. I am making it a generalized, so on up to nk. Let's suppose there are k number of these congruent relations. First we are going to find this n. The second step is to find y. So here I am going to write yi. So it is y1 y2 for each and every this relation. So your y would be capital N, this N divided by Ni, the current N, for all N varying from I to K. You are going to find the yi for each this I term. Then the third step is to find zi that is equal to y inverse mod Ni. Fine. So now the fourth step in Chinese remainder theorem is that is x that is equal to ai. Okay, so here the summation of I varying from 1 to k, we are going to use the summation for all I. So that is ai into yi into zi, and that would be whole mod capital N. So this is way to solve for the x with the Chinese remainder theorem. So this theorem we are going to use to solve in RSA algorithm. So here we already discussed that how to find the inverse. So here the previous video in which we have learned that how to find the inverse with the Euclidean algorithm. So we are going to apply that thing over here. So now let's take an example to solve these relations by taking some example. Okay. So let me choose one example. Okay, so let's take an example. X is congruent to 2 mod 3, then x is congruent to 3 mod 5, 3 mod 5, then x is congruent. We are having the three equations over here, congruent equation over here, 2 mod 7. Now our aim is to find the x. So now the first step is find n, that is equal to, now just mark it, this is your a1, n1, this is your a2, n2, this is your a3, and this is your n3. So here n1 is equal to n1 into n2 into n3. So that would be 21 into 5, 105. So here we are having a n is equal to 105. So the second step is to solve yi. So here we are going to calculate y1 first, that is n upon n1, n1 is a 3, so that would be 3 into 5 into 7 upon 3, so that would become 35. Similarly, we are going to calculate y2, that would be 21, skipping this 5. Similarly, y3, that would be 15. So second step we are done. So now we are going to calculate the third step. In the third step, we are going to find the z1. So z1 that is equal to y inverse, that is 35 inverse mod ni, current n is 3, mod 3. So this is your z1, z2 that is equal to 21 mod 5, and z3 that would be 15 mod 7. So here to solve this we are going to apply the Euclidean algorithm. So we are having 35 and 3. So let me borrow some space from here. Okay. 35 and 3. So 35, that is equal to 3 into 11, that would be 33, 34, 35. We are having a 2 over here, so that would be minus. So now, 21 and 5. So let's have a 21, that is equal to 5 4s are 20 plus 1. Again, correctly we will have a 1 over here. So 1 is equal to 21 minus 5 into 4. Okay. So okay, I forgot to put the inverse over here. Okay. So according to this y inverse. So here should be inverse. Okay, taking a mod on both sides, 1 mod 5, that is equal to 21 mod 5, again multiple of 5, that would be 0. So here 25 is a multiplication, that would be 1 upon 21 mod 5, that is equal to 1 mod 5. So 1 mod 5 is a 1. So here Z2, that is equal to 1. Okay, Z3, that is equal to 15 inverse 15 and 17. 15, that is equal to 7 to the 14 plus 1 15. Okay, so here simple again, simple 1, that is equal to 15 minus 7 into 2, taking a mod of a 7, 1 mod 7, that is equal to 15 mod 7, multiple of 7 again 0, so 15 would be here, that would be 1 mod 7, similar to the previous one. So I think we have made a mistake in the very first one, so let's check it again. 35 and 3, so let's 35, that is equal to 3 into 11, 33 plus 35, 2, that is 2. So again taking a 3 and 2, 3, that is equal to 2 into 1 plus 1. Okay, 1 remainder. Okay, GCD we already learned. Okay, so now 1, that is equal to 3 minus 2, 3 minus 2, putting a value of a 2, that is 35 minus 3 into 11. So okay, that would be 3 minus 35 plus 3 into 11. Okay, so this is 3 into 11, taking a 3 both sides from this 3, that is equal to 1 plus 11 minus 35, so that would be 12 into 3 minus 35. Okay, so now we are having this. Now taking mod on the both sides with respect to 3, 1 mod 3, that is equal to, so that would be 0 minus 35 mod 3. So here we are having this equation. So I'm going to erase the upper part. Okay, so here okay, we are going to have a 35 in inverse order. So 1 upon 35 mod 3, 35 would be here. So that would be minus 1 mod 3. So here we are having this answer, that would be minus 1 into 3, 3 minus 1 minus 3 plus that is 2. So here we get a mistake. So here should be 2. So that is I think the last time we have missed this negative sign. So you should be very clear with the sign when you are going to evaluate in this manner. Okay, so now we have calculated all the z values. Now the fourth step is to multiply a, y and z. So k, here k is a 3, so 3 values. Okay, a1, y1, z1. So a1 is a 2, x, that is equal to 2 into a1, y1, 35 into a1, y1, z1, that is again 2. Okay, plus a2, that is 3 into 0 1 okay, by 2 21, 3 into 21 into 1 plus a 2 2 y 15 z 1. So here we are having this equation. So we already implemented this 4 step. So I'm going to raise these 4 steps. Okay. So now let's solve this, and at last we are having a mod n according to the steps. So here mod n is 105, n is 105. Okay, so here you can write okay, 70 to 140, 140. You can segregate the mod now. Mod 105 plus 3 1 the 3 3 2 the 6. Mod 105 plus 30 mod 105. So here we are having 35, right? 140 105 105, and remainder is 140 minus 105. So we are in the 35. This is again 63. Your value should be always less than 105 in this case. 35 plus 63 plus 30. So that's why we are taking again mod 105, because your value should be always less than 105 in this case. So we are having a 358, 336, 612, 128 mod 105. So that would be our answer. 128, 105, 105, 6, 7, 8. So we are having a 13. Sorry, here we are having a 23. So that is 23. So value of our x is 23 in this case. So now this is a minimum value. So these all the congruent equation can be defined with the 23 into I. So your I will varying from 1 up to whatever you want, fine. So this 23 is the bare minimum value. So this was our Chinese remainder theorem. So in this video lecture we have learned the special case of Chinese remainder theorem and how to solve the congruency with the Chinese remainder theorem. So this is all for now. In the next video lecture we are going to learn the RSA algorithm, in which these things are very much useful. So if you like this video, just hit a like button and subscribe to my YouTube channel so that you will get an update regarding my latest video lecture. If you are having any doubt, you can ask in the description below. Thanks for watching. Take care.